Tonight, we're going to look at the strangest second in the history of the universe. Not the first millisecond, not the first day, not the first year, the first second. The single second that, by every careful measurement modern cosmology has produced, contains more events, more transformations, more new structures than the entire 14 billion years that came after it. In 1 second, the universe went from a state where the four fundamental forces of nature were unified into a single mathematical entity, to a state where they had split into the four distinct forces we recognize today. In 1 second, the universe went from a hot, dense soup of free quarks and gluons to a sea of protons and neutrons. In 1 second, the universe went from a state where matter and antimatter existed in nearly equal amounts to a state where matter had won, by a margin of about 1 part in a billion. In 1 second, the universe became the kind of place where atoms could eventually form, where stars could eventually burn, where planets could eventually orbit, where life could eventually emerge. By the end of tonight, we're going to walk through what happened in each tiny fraction of that first second, beginning with the mysterious Planck epoch, where our current physics breaks down, the cosmic inflation that stretched space by a factor of more than 10 to the 26 in roughly 10 to the minus 32 seconds. The symmetry breaking that separated the fundamental forces from a single unified force into the four distinct forces we observe today. The electroweak phase transition that gave mass to fundamental particles through the Higgs mechanism, the quark-gluon plasma that filled all of space at temperatures of trillions of degrees, the moment quarks were trapped inside protons and neutrons through the quark-hadron transition, the asymmetry between matter and antimatter that determined whether anything could exist at all, the decoupling of neutrinos that produced a cosmic neutrino background still drifting through us today, the electron-positron annihilation that left only a small excess of matter behind, and what the universe actually looked like at the exact moment 1 second after the Big Bang, just before Big Bang nucleosynthesis would begin to forge the first atomic nuclei. If you're enjoying tonight's slow drift through the cosmos, consider subscribing. We make long, careful sleep documentaries about the deep moments in cosmic history, the structures that emerged from impossibly small fractions of a second, the fundamental forces that separated from a single unified force, and the patient theoretical and experimental work that has, over the past century, reconstructed what was happening in those first instants. Your support helps us keep making them. What we are about to explore is, by every honest estimate, one of the most extraordinary stretches of time in the history of the universe. Not because it was particularly long in any human-relevant sense. It was, by every clock we could imagine, a single second, but that single second contained more transformations, more new structures, more fundamental physics than the next 14 billion years combined. The universe at the beginning of that second was unrecognizable. The universe at the end of that second was, in many fundamental respects, the universe we still inhabit today. Tonight, we will trace each step of that transformation, walking through the cosmic timeline at increasingly long timescales as the universe cooled and the basic structures of physics emerged. Now, let's begin. Let's talk about cosmic inflation first, because that is where the story really starts. The Big Bang itself as a cosmological event was not a single instant. It was a process. The earliest moments are, by every careful description, the most mysterious. The physics we currently understand cannot fully describe the universe before about 10 to the minus 43 seconds, a duration called the Planck time. At those timescales, our theories of gravity and quantum mechanics, which work beautifully in their respective regimes, cease to be compatible with each other. The universe before the Planck time would require a complete theory of quantum gravity to describe, and we do not yet have such a theory. But after the Planck time, the physics becomes, by every careful estimate, much more tractable. From about 10 to the minus 43 seconds onward, we have well-developed theoretical frameworks that describe what was happening, and we have experimental tests that confirm large parts of those frameworks. The earliest period we can describe with confidence is what cosmologists call cosmic inflation. Inflation was proposed in 1980 by Alan Guth, then a young physicist at the Stanford Linear Accelerator Center. Guth was trying to solve several puzzles about the early universe. One was the horizon problem, the question of why the universe appears so uniform on large scales when different parts of it could not have been in causal contact in standard Big Bang cosmology. Another was the flatness problem, the question of why the geometry of space appears almost exactly flat when small deviations from flatness should have grown enormously over cosmic time. A third was the monopole problem, the question of why we do not observe magnetic monopoles which grand unified theories predict should have been produced in abundance in the early universe. Guth's insight was that all three problems could be solved if the very early universe had undergone a brief period of exponential expansion. During this period, called inflation, space itself expanded at a rate that doubled the size of any region many times in quick succession. The total expansion in the standard inflationary models was by a factor of at least 10 to the 26. In some versions, the expansion was by a factor of 10 to the 60 or more. The exact amount is still under investigation, but the basic picture is that space stretched enormously in an extraordinarily brief time. The duration of inflation in most models was approximately 10 to the minus 32 seconds. That is, the inflationary period lasted for 100 million trillion trillionths of a second. In that period, the universe expanded by a factor of at least 100 trillion trillion. The expansion rate during inflation was, by every careful estimate, far faster than the speed of light. This does not violate the laws of physics, because space itself is expanding, not material objects moving through space. After inflation ended, the universe entered a phase called reheating. The energy that had driven inflation, stored in a hypothetical inflaton field, was converted into the particles and radiation that filled the post-inflationary universe. The reheating process is, by every honest description, still not fully understood in detail, but it was the bridge between the inflationary epoch and the hot, dense early universe that conventional Big Bang physics describes. But here's the thing most people don't realize about inflation. It was not a uniform, smooth expansion. Quantum fluctuations during inflation produced tiny variations in the density of matter and energy. These variations were stretched by the rapid expansion to macroscopic scales. They became, in the post-inflationary universe, the seeds of all later cosmic structure. Every galaxy, every cluster of galaxies, every cosmic filament we observe today began as a quantum fluctuation during inflation. The cosmic structure of the present-day universe is, in this sense, a magnified fossil of quantum mechanics operating in the first fraction of a second. The evidence for inflation comes from multiple independent observations. The cosmic microwave background, the relic radiation from about 380,000 years after the Big Bang, shows a pattern of temperature variations that matches what inflation predicts. The variations are nearly scale invariant, meaning they appear in roughly the same amounts at all spatial scales, which is exactly what inflation produces. The variations are also slightly tilted, with slightly more power at larger scales, which inflation also predicts, and which has been measured. Inflation is not, by every careful description, fully proven. The exact inflaton field has not been identified. The duration of inflation, the energy scale, and the specific particle responsible are all still being investigated. But the basic framework is, by every careful estimate, broadly consistent with the observations, and it solves several puzzles that the standard Big Bang model could not solve on its own. The Planck satellite, operating from 2009 to 2013, produced the most precise measurements of the cosmic microwave background ever obtained. The data is, by every careful analysis, consistent with the predictions of simple inflationary models. The next generation of CMB experiments, including the Simons Observatory and CMB-S4, will probe the inflationary signal at even higher precision, potentially detecting the primordial gravitational waves that inflation also predicts. If those gravitational waves are detected, it would be one of the most direct pieces of evidence we could have for inflation. For now, the first 10 to the minus 32 seconds of cosmic history are described by inflation. The universe started in some quantum gravitational state we cannot fully describe, transitioned through the Planck epoch, and then entered inflation. During inflation, space expanded by an enormous factor, and the seeds of all cosmic structure were planted. By the end of inflation, the universe was filled with hot, dense particles and radiation, ready for the next phase of cosmic evolution. The story of how inflation was developed as a theoretical framework is, in some ways, characteristic of how modern theoretical physics works. Alan Guth, when he proposed the idea in 1980, was not initially aware that he was solving multiple cosmological problems at once. He was working on a question about magnetic monopoles in grand unified theories. The realization that exponential cosmic expansion could solve the monopole problem, the horizon problem, and the flatness problem all at once came gradually, as he and other physicists worked out the implications. Guth's original model of inflation, sometimes called old inflation, had technical problems. The transition from the inflationary phase to the post-inflationary universe was, in the original model, too violent and too inhomogeneous. The universe that emerged from old inflation would have looked nothing like what we observe today. The model needed revision. Andrei Linde, at the Lebedev Physical Institute in Moscow, proposed a revised version called New Inflation in 1982. Linde's model had a different form of the inflaton field potential that allowed for a smoother exit from inflation. This version was, by every careful analysis, more consistent with the cosmological observations. Linde later developed several other versions of inflation, including chaotic inflation and eternal inflation, each with different specific features. Paul Steinhardt and Andreas Albrecht independently developed similar ideas at about the same time. The new inflation model, with its various variants, became the standard framework for thinking about the inflationary period. Over the subsequent decades, many specific inflationary models have been proposed, each with slightly different predictions for the spectrum of primordial fluctuations, the amount of inflation that occurred, and the post-inflationary reheating. The exact identity of the inflaton field, the scalar field whose energy drove inflation, is still unknown. The Higgs field, which is the only confirmed fundamental scalar field in the standard model, has been proposed as a candidate, but the simplest Higgs inflation models are difficult to reconcile with the measured Higgs boson mass. Other proposed inflaton candidates include various extensions of the standard model, supersymmetric particles, axion-like fields, and fields from string theory. None of these has yet been confirmed. The detection of primordial gravitational waves, sometimes called B-mode polarization, in the cosmic microwave background would be one of the most direct pieces of evidence for inflation. Inflation predicts that gravitational waves should have been produced during the inflationary period, and that these waves should have left a specific polarization signature on the cosmic microwave background. The BICEP experiments at the South Pole, the Simons Observatory, and the planned CMB S4 experiment are all looking for this signature. As of 2026, no detection has been made, but the experimental limits are tightening. If inflation occurred at relatively high energy scales, the primordial gravitational waves should be detectable in the next decade. If primordial gravitational waves are detected, it would confirm the inflationary framework at a level comparable to the discovery of the Higgs boson. The detection would also tell us the energy scale of inflation, which is currently unknown. The combination of these pieces of evidence would, by every careful estimate, transform our understanding of the very early universe. The amount of expansion that occurred during inflation is, in some sense, almost incomprehensible. A factor of 10 to the 26 is 100 trillion trillion. If you started with an object the size of a single atomic nucleus, expanding by this factor would produce an object larger than the visible universe today. The inflationary expansion took a tiny patch of pre-inflationary space-time and stretched it to enormous scales. The entire observable universe today, with its hundreds of billions of galaxies and trillions of stars, is, in some sense, the inflated descendant of a single tiny patch of the pre-inflationary universe. This stretching had a remarkable consequence. The pre-inflationary universe was, by every careful theoretical estimate, almost certainly not uniform. It contained variations in density, temperature, and other properties that varied from place to place. When inflation stretched a tiny patch to cosmic scales, the patch became almost perfectly uniform. The variations that existed were stretched to scales beyond the cosmic horizon, where they could not affect local physics. The resulting universe after inflation was approximately uniform on large scales, with only the small quantum fluctuations that occurred during inflation imprinted on the smooth background. This uniformity is, by every careful measurement, exactly what we observe in the cosmic microwave background. The temperature of the CMB is the same in every direction to about 1 part in 100,000. The small variations at the level of microkelvin are the imprints of the quantum fluctuations during inflation. The pattern of these variations encodes detailed information about the inflationary epoch and about the subsequent cosmic evolution. The amount of expansion needed to solve the horizon problem, the flatness problem, and the monopole problem is, by every careful theoretical calculation, approximately a factor of 10 to the 25 or more. The various inflationary models predict slightly different amounts of total expansion. The observed cosmic uniformity is consistent with the expansion being at least this large. Whether the expansion was much larger, perhaps by many additional orders of magnitude, is, by every honest description, still under investigation. Let's consider the grand unified theory epoch next. The period before inflation, when the universe was so hot that 3 of the 4 fundamental forces were unified into a single force. The Planck epoch, before about 10 to the minus 43 seconds, is where quantum gravity dominates and our current physics breaks down. After the Planck time, but before inflation, the universe entered what cosmologists call the grand unified theory epoch. The four fundamental forces of nature in modern physics are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. In our everyday experience, these forces are very different from each other. Gravity holds planets in orbit and shapes large-scale cosmic structure. Electromagnetism governs chemistry and the behavior of atoms. The weak force is responsible for certain types of radioactive decay. The strong force binds quarks into protons and neutrons. But the standard model of particle physics, which describes three of these forces, also tells us that they are deeply related. At sufficiently high energies, the electromagnetic and weak forces merge into a single force called the electroweak force. This was demonstrated experimentally at CERN in the late 1970s and early 1980s with the discovery of the W and Z bosons that mediate the weak force. The energy at which the electroweak force unifies is approximately 100 GeV, which corresponds to a temperature of approximately 10 to the 15 Kelvin. At even higher energies, theoretical extensions of the standard model predict that the electroweak force unifies with the strong force into a single grand unified force. The energy at which this happens is approximately 10 to the 16 GeV, which corresponds to temperatures of approximately 10 to the 28 Kelvin. This is far beyond the energies our particle accelerators can reach, so the gut scale physics has not been directly tested. But the cosmological evidence is consistent with there having been a gut epoch in the early universe. The gut epoch, in the standard cosmological model, occurred between approximately 10 to the minus 43 seconds and 10 to the minus 36 seconds. During this period, the universe was so hot that the electromagnetic, weak, and strong forces were unified. Only gravity was distinct. The fundamental particles of nature did not yet have the diverse properties we observe today. Quarks and leptons were related to each other by the larger symmetry of the gut. At the end of the gut epoch, as the universe expanded and cooled, the gut symmetry was broken. The strong force separated from the electroweak force. Various heavy particles predicted by the gut were produced and then mostly decayed. The decay of these heavy particles may have played a role in baryogenesis, the asymmetry between matter and antimatter that we will discuss in more detail later. The transition out of the gut epoch was a kind of cosmic phase transition. It was, in some ways, analogous to water freezing into ice. As the universe cooled past the critical temperature, the symmetric phase became unstable, and the universe transitioned into the broken symmetry phase that we observe today. The transition produced topological defects, including the magnetic monopoles that the original Big Bang model predicted should be common. The fact that we do not observe these monopoles is one of the original problems that inflation solved. The inflationary expansion diluted any monopoles produced during the gut phase transition to undetectable densities. But here's the thing most people don't realize about the gut epoch. It is, in some sense, our best window into physics beyond the standard model. The temperatures during the gut epoch correspond to energies that we will never be able to reach in particle accelerators on Earth. The Large Hadron Collider operates at energies of about 10,000 GeV, which is 12 orders of magnitude below the gut scale. The only way to test gut-scale physics is through cosmological observations of the early universe. The Big Bang is, in this sense, our only particle accelerator that can probe energies that high. The specific grand unified theory that describes nature at these energies is, by every honest description, not yet known. Multiple candidate guts have been proposed. The simplest is called SU5. proposed by Howard Georgi and Sheldon Glashow in 1974. More elaborate versions include SO10, E6, and various supersymmetric extensions. Each predicts slightly different particle content and different rates of proton decay, the very slow radioactive decay of protons that GUTs predict. Experimental searches for proton decay, including the Super Kamiokande experiment in Japan and the planned Hyper Kamiokande, have so far not detected any decay. The current lower limit on the proton lifetime is approximately 10 to the 34 years. This rules out some GUT models and constrains others. The full picture of GUT-scale physics will, by every careful estimate, take decades more to clarify. New experimental data from proton decay searches, from cosmological observations of inflation, and from particle physics at lower energies will all contribute. The first second after the Big Bang, particularly the very earliest period, was the regime where GUT-scale physics was actively operating. Understanding that period is one of the deepest open problems in physics. The connections between GUT-scale physics and quantum gravity are also worth considering. The Planck scale, where quantum gravity becomes important, is at energies of approximately 10 to the 19 GeV. The GUT scale is at approximately 10 to the 16 GeV, only 3 orders of magnitude below the Planck scale. The two regimes are not far apart in physics terms, although they are far apart in particle accelerator terms. Some theoretical frameworks attempt to unify the duty and quantum gravity scales into a single description. String theory, for example, predicts a fundamental scale at or near the Planck energy, with the various forces emerging from the internal structure of strings at lower energies. Loop quantum gravity, an alternative approach, focuses primarily on quantum gravity, but has implications for high-energy unified physics. M-theory, the 11-dimensional generalization of string theory, similarly addresses both regimes simultaneously. None of these unified theoretical frameworks has been experimentally confirmed. They make various predictions, some of which could be tested by future cosmological observations or by extreme particle physics experiments. The relationship between the GUT epoch and the Planck epoch is, in this sense, one of the most active research areas in fundamental theoretical physics. The first instance of cosmic history are the regime where these unified theories would be most directly relevant. The earliest fraction of a second of cosmic history is, in some sense, where modern fundamental physics meets cosmology most directly. The questions about the unification of forces, the nature of quantum gravity, the origin of cosmic inflation, and the specific properties of the inflaton field are all questions that can, in principle, be addressed by combining particle physics, theoretical physics, and cosmological observations. The first second of the universe is the natural arena for all of these investigations. Let's talk about the electroweak transition next, because it happened about 10 to the minus 12 seconds after the Big Bang during the first second, and it is one of the few early universe events that we can study directly in particle accelerators today. After the Guti symmetry was broken and the strong force separated from the electroweak force, the universe entered the electroweak epoch. During this period, lasting from approximately 10 to the minus 32 seconds to approximately 10 to the minus 12 seconds, the electromagnetic and weak forces remained unified. The temperature was very high, on the order of 10 to the 15 Kelvin at the beginning, dropping as the universe expanded and cooled. The electroweak transition occurred when the temperature dropped to about 100 GeV, or roughly 10 to the 15 Kelvin. At this temperature, the electroweak symmetry was broken, and the electromagnetic and weak forces became distinct. The mechanism for this symmetry breaking is called the Higgs mechanism, named after Peter Higgs and other physicists who developed the theoretical framework in the 1960s. The Higgs mechanism works by introducing a scalar field, called the Higgs field, that pervades all of space. At very high temperatures, the Higgs field has an expectation value of 0, and the electroweak symmetry is unbroken. As the universe cools, the Higgs field undergoes a phase transition, and its expectation value becomes non-zero. The non-zero Higgs field breaks the electroweak symmetry. Particles that interact with the Higgs field acquire mass. Particles that do not interact with the Higgs field remain massless. The Higgs boson, the quantum excitation of the Higgs field, was discovered at the Large Hadron Collider in 2012. The discovery confirmed the basic picture of the electroweak transition and the Higgs mechanism. The Higgs boson has a mass of approximately 125 GeV, slightly higher than the electroweak transition temperature. Its discovery was, by every careful estimate, one of the major scientific achievements of the early 21st century. The cosmic moment when the electroweak symmetry broke is, in some sense, the moment when mass began to exist in the universe. Before the transition, the fundamental particles of nature did not have rest masses. They were all moving at the speed of light, like photons. After the transition, most particles acquired mass through their interactions with the Higgs field. The masses of quarks, leptons, and the W and Z bosons all derive from this mechanism. The transition was, by every careful estimate, very rapid. The universe at this stage was expanding extremely quickly, and the temperature was dropping correspondingly. The phase transition occurred over a brief interval, perhaps lasting only 10 to the minus 11 or 10 to the minus 10 seconds. Within that brief moment, the universe transformed from a state where mass did not exist to a state where most particles had the masses we observe today. But here's the thing most people don't realize about the electroweak transition. It is the only early universe phase transition that we can currently reproduce in the laboratory. The Large Hadron Collider, by colliding protons at extremely high energies, can briefly create conditions similar to those just after the electroweak transition. The W and Z bosons produced in these collisions are direct probes of the broken electroweak symmetry. The Higgs boson, also produced in collisions, is the smoking gun of the symmetry-breaking mechanism. The LHC and its successors will continue to probe electroweak physics in great detail. The next major LHC upgrade, the High Luminosity LHC, will begin operations in 2029. It will collect approximately 10 times more data than the original LHC, allowing precision measurements of the Higgs boson properties and searches for any new physics beyond the standard model. Future colliders, including proposed future circular collider designs at CERN and the International Linear Collider, will probe even higher energies. Through these experiments, we are in the unusual position of being able to directly study, in our laboratories on Earth, conditions that existed in the universe 1/trillionth of a second after the Big Bang. The electroweak transition is, in this sense, the only early universe event that we can currently access experimentally. Everything earlier than 10 to the minus 12 seconds is beyond the reach of our particle accelerators, and we can only study it through cosmological observations of its consequences. The history of how the electroweak unification was discovered is worth pausing on. The theoretical framework was developed in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg. They proposed that the electromagnetic force and the weak nuclear force, which appear very different at everyday energies, are actually different manifestations of a single underlying electroweak force at sufficiently high energies. The theory predicted the existence of W and Z bosons, the mediators of the weak force, with specific masses. The W and Z bosons were discovered at CERN in 1983, with the W boson at approximately 80 GeV and the Z boson at approximately 91 GeV. The discovery, led by Carlo Rubbia and Simon van der Meer, won the Nobel Prize in Physics in 1984. The masses of the W and Z bosons matched the theoretical predictions, confirming the electroweak unification. The Higgs boson, the final missing piece of the electroweak theory, was predicted in 1964 by several independent groups including Peter Higgs, François Englert, Robert Brute, Gerald Guralnik, Carl Hagen, and Tom Kibble. The detailed mechanism by which the Higgs field gives mass to other particles was worked out over the subsequent years. The mass of the Higgs boson itself, however, was not predicted by the theory and had to be determined experimentally. The search for the Higgs boson became one of the central goals of high-energy physics for several decades. The Large Electron-Positron Collider at CERN, operating in the 1990s, did not find the Higgs but set lower limits on its mass. The Tevatron at Fermilab, operating from 1983 to 2011, also searched for the Higgs without finding it. The Large Hadron Collider, with its much higher energies, finally discovered the Higgs in 2012. The discovery was announced jointly by the ATLAS and CMS experiments. Peter Higgs and François Englert shared the 2013 Nobel Prize for the theoretical prediction. The Higgs boson mass of 125 GeV is, by every careful estimate, almost exactly in the middle of the range that the Standard Model allows. If the Higgs were significantly lighter, the Standard Model would have predicted instability of the electroweak vacuum. If the Higgs were significantly heavier, certain consistency conditions of the theory would have been violated. The fact that nature has chosen a mass that is consistent with the Standard Model, but at the edge of its allowed range, is, in some sense, both a confirmation of the theory and a hint that there may be additional physics at higher energies. The High Luminosity LHC, the upcoming upgrade scheduled to begin operations in 2029, will measure the Higgs boson properties with unprecedented precision. The Higgs couplings to various fermions, the Higgs self-interaction, and any deviations from Standard Model predictions will all be measured. These precision measurements will, by every careful estimate, either confirm the Standard Model picture of the electroweak transition or reveal hints of new physics that would have been important in the very early universe. Let's pause and consider the quark-gluon plasma next, because between the electroweak transition and the first second, the universe was filled with this exotic state of matter that we can also recreate in our laboratories. Between approximately 10 to the minus 12 seconds and approximately 10 to the minus 6 seconds, the universe was in the quark epoch. Temperatures were too high for quarks to bind together into protons and neutrons. Instead, the universe was filled with a hot, dense plasma of free quarks and gluons, along with electrons, neutrinos, and other particles. Quarks are the fundamental constituents of protons and neutrons. There are 6 known types of quarks: up, down, strange, charm, bottom, and top. In the universe today, quarks are always bound together into composite particles called hadrons. Protons consist of 2 up quarks and 1 down quark. Neutrons consist of 2 down quarks and 1 up quark. Heavier hadrons can contain other types of quarks. Free, isolated quarks are never observed in nature. This is called color confinement, and it is one of the most striking features of the strong nuclear force. In the quark-gluon plasma, however, the temperature is so high that the strong force is too weak to confine quarks. The quarks roam freely through space, interacting with each other and with the gluons that mediate the strong force. The plasma is in many ways similar to an ordinary fluid, with definable properties like density, pressure, temperature, and viscosity. But the constituents are quarks and gluons, not atoms or molecules. The temperature of the early universe quark-gluon plasma was approximately 10 to the 13 Kelvin, or about 10 trillion degrees. The density was extraordinary, far higher than anything in the present-day universe. Every cubic centimeter of space contained more energy than the entire output of the Sun over its 10 billion-year lifetime. The quark-gluon plasma has been recreated in particle accelerators on Earth. The relativistic heavy-ion collider at Brookhaven National Laboratory in New York, which began operations in 2000, was the first facility to do so. The accelerator collides nuclei of heavy elements like gold or uranium at extremely high energies. The collisions briefly produce a tiny droplet of quark-gluon plasma, lasting for less than 10 to the minus 22 seconds before it cools and the quarks recombine into hadrons. The LHC has also recreated the quark-gluon plasma through heavy ion collisions beginning in 2010. The LHC collisions produce plasma at even higher temperatures than RHIC. The properties of the plasma can be studied by analyzing the particles that emerge from each collision and tracking how they moved through the plasma before recombining. The results of these experiments have been, by every careful estimate, surprising. The quark-gluon plasma turned out to be not the gas-like substance that early theoretical models predicted. Instead, it is a nearly perfect fluid with extremely low viscosity. The viscosity is, by every careful measurement, close to the theoretical minimum allowed by quantum mechanics. This makes the plasma one of the most fluid substances ever observed. The behavior of the quark-gluon plasma reveals important properties of the strong force at high temperatures. It tells us how quarks and gluons interact when they are not confined inside hadrons. It tells us about the phase structure of QCD, the theory of the strong force, and it tells us about what conditions were like in the early universe during the quark epoch. But here's the thing most people don't realize about the early universe quark-gluon plasma. It was not a brief moment, it was a substantial fraction of the first second. In standard cosmology, the universe was in the quark epoch from about 10 to the minus 12 seconds to about 10 to the minus 6 seconds. That is 6 orders of magnitude in time. During this period, the universe was, in volume, expanding and cooling, but the quark-gluon plasma was the dominant state of matter throughout. Cosmologically speaking, the quark epoch was the longest single phase of the early universe up to that point. The detailed properties of the early universe quark-gluon plasma are, by every careful estimate, still being investigated. The heavy ion collision experiments produce plasma droplets that are much smaller and shorter-lived than the cosmic plasma. Whether the properties scale up to the cosmic case in straightforward ways is, by every careful estimate, still being established. The investigations will continue at RHIC, the LHC, and at future facilities including the proposed electron-ion collider. The discovery that the quark-gluon plasma behaves as a nearly perfect fluid was, by every careful estimate, one of the most surprising results in particle physics over the past 2 decades. The pre-experimental expectation based on simple theoretical models was that the plasma at very high temperatures would behave like a gas, with the quarks and gluons moving freely and interacting only through occasional weak collisions. The experimental results showed instead a strongly coupled fluid, with the quarks and gluons interacting so strongly that the bulk behavior was fluid-like rather than gas-like. The viscosity of the quark-gluon plasma, when expressed in units appropriate to its temperature and density, is approximately 1/10 of the theoretical minimum allowed by quantum mechanics. This minimum, called the KSS bound after Kovtun, Sun, and Starinets, who derived it from string theory considerations, is the lowest possible viscosity for any physical fluid. The quark-gluon plasma is the closest known substance to this theoretical minimum, far below the viscosity of water, liquid helium, or any other fluid found in nature. The implications of this low viscosity extend beyond just the early universe. The discovery has connections to string theory through the ADS-CFT correspondence, a theoretical framework that relates certain strongly coupled gauge theories to weakly coupled gravitational theories in higher dimensional spaces. The quark-gluon plasma is, in this sense, a natural laboratory for testing ideas about strongly coupled quantum systems, with applications ranging from cosmology to condensed matter physics to fundamental string theory. The detailed behavior of the early universe plasma, as the universe expanded and cooled, also has implications for cosmic structure. As the plasma temperature dropped, the speed of sound waves in the plasma changed. These sound waves are the precursors of the baryon acoustic oscillations that we observe today as a feature in the galaxy distribution. The phase of the sound waves at the moment of the quark-hadron transition and at later cosmic moments was preserved in the eventual large-scale structure of the universe. The structure we observe today is, in this sense, partially shaped by the dynamics of the quark-gluon plasma during the first second. The detailed temperature of the quark-gluon plasma at various cosmic moments can be calculated quite precisely. At 10 to the minus 12 seconds, just after the electroweak transition, the temperature was approximately 10 trillion Kelvin. At 10 to the minus 10 seconds, it had dropped to about 1 trillion Kelvin. At 10 to the minus 8 seconds, perhaps 100 billion Kelvin. The plasma cooled continuously as the universe expanded, with the temperature dropping by a factor of about 2 for every doubling of the cosmic scale factor. The composition of the plasma also changed continuously with temperature. At very high temperatures, all 6 known quark flavors were present in approximately thermal abundances. As the temperature dropped below the rest mass of the top quark, approximately 170 GeV in energy units, the top quarks could no longer be efficiently created, and they began to decay or annihilate. Similar mass thresholds caused the bottom, charm, and strange quarks to gradually disappear from the plasma as the temperature dropped. By the time of the quark-hadron transition, the plasma contained primarily up and down quarks, the lightest 2 flavors. The same logic applied to other particle species. At very high temperatures, all the particles of the Standard Model were present in thermal abundance. As the temperature dropped past each particle's rest mass, that particle could no longer be efficiently produced, and it gradually disappeared from the thermal plasma. The Higgs boson, the W and Z bosons, the top quark, and the heavier leptons all dropped out of equilibrium at various early universe temperatures. By the end of the first second, only the very light particles remained in significant numbers. The future heavy ion programs at the LHC and at proposed future facilities will continue to map out the properties of the quark-gluon plasma at various temperatures and energy densities. The recently approved electron-ion collider in the United States, scheduled to begin operations in the early 2030s, will study a related but distinct regime of QCD physics, focusing on how quarks and gluons are distributed inside protons and other hadrons. The combination of heavy ion experiments at the LHC and electron-ion experiments at EIC will, by every careful estimate, give the most complete picture of QCD physics ever assembled, with direct relevance to understanding the cosmic plasma of the first second. Let's consider quark confinement next. At approximately 10 to the minus 6 seconds after the Big Bang, when the universe had cooled to a temperature of approximately 1 trillion Kelvin, the quark-gluon plasma underwent a phase transition. The temperature dropped below the threshold at which the strong force could no longer keep quarks from binding into hadrons. The quarks, previously free to roam, were trapped into protons, neutrons, and other composite particles. The cosmic plasma transformed into a gas of hadrons. This transition, called the quark-hadron transition or hadronization, is one of the most important phase transitions in cosmic history. Before it, the universe was filled with free quarks and gluons. After it, the universe contained the particles that would later combine into atoms. The fundamental constituents of all subsequent matter, the protons and neutrons that make up every atomic nucleus, were first formed during this transition. The exact mechanism of hadronization in the early universe is, by every careful description, complicated. The transition is, in lattice QCD calculations, a crossover rather than a sharp first-order phase transition. As the temperature drops past the critical value, the system gradually transitions from the quark-gluon plasma phase to the hadron gas phase. The exact temperature of the crossover, derived from theoretical calculations and heavy ion collision experiments, is approximately 150 MeV, corresponding to about 1.7 trillion Kelvin. Once hadronization was complete, the universe contained a mixture of protons, neutrons, and various heavier hadrons. The heavier hadrons quickly decayed into protons and neutrons. The lighter hadrons, including pions, also decayed quickly into other particles. By the end of the hadronization process, the universe was filled with protons, neutrons, electrons, positrons, neutrinos, antineutrinos, and photons. The number densities of each species are, by every careful calculation, determined by the temperature and the thermodynamic properties of the standard model particles. The number of quarks in the universe at the moment of hadronization is, by every careful estimate, the same as the number of protons and neutrons that emerged from the hadronization process. The quarks were not created or destroyed during hadronization, just rearranged into composite particles. The slight asymmetry between quarks and antiquarks, established by baryogenesis at earlier times, was preserved through the hadronization process. But here's the thing most people don't realize about the quark-hadron transition. The number of protons and neutrons that emerged was tiny compared to the total number of particles in the universe. For every proton or neutron, there were approximately 10 billion photons. The matter content of the universe was, even at this early stage, dominated by radiation. Photons outnumbered baryons by a factor of about 10 to the 10. This ratio, called the baryon-to-photon ratio, is one of the fundamental parameters of cosmology. It is set by the baryogenesis process at earlier times, and it determines many aspects of subsequent cosmic evolution, including the abundances of light elements produced during Big Bang nucleosynthesis. The cosmic moment of hadronization is, in some sense, when the first matter we would recognize today was formed. Protons and neutrons emerged from the previously chaotic plasma. Composite particles distinguishable from each other by their constituent quarks came into existence. The conditions for the eventual formation of atoms, stars, and galaxies were being established. The detailed dynamics of the early universe hadron gas are themselves worth pausing on. Just after the quark-hadron transition, the universe contained not just protons and neutrons, but also heavier hadrons like pions, kaons, hyperons, and various other particles. These heavier hadrons quickly decayed through the weak nuclear force, transforming into lighter particles and ultimately into protons, neutrons, electrons, neutrinos, and photons. The decay processes released energy into the cosmic plasma, contributing to the overall thermal balance. The ratio of protons to neutrons in the universe at this stage was, by every careful calculation, determined by the rates of weak interactions converting one into the other. At very high temperatures, the conversion rates were fast compared to the cosmic expansion rate, and the ratio was approximately equal. As the universe cooled, the conversion rates slowed, and the ratio shifted toward more protons than neutrons because protons are slightly lighter and therefore energetically favored. By the end of the first second, when neutrinos decoupled, the proton-to-neutron ratio was approximately 7:1. This ratio is one of the key parameters that determines the eventual abundance of light elements produced during Big Bang nucleosynthesis. The fact that the ratio is set primarily by physics during the first second is, by every careful estimate, one of the reasons why measurements of the light element abundances tell us so much about the conditions in the first second. The detailed kinetics of these weak interactions has been studied extensively in particle physics laboratories. The cross-sections for the relevant reactions, including neutron beta decay and various scattering processes involving neutrinos, are known to high precision. The same cross-sections that are measured in laboratories today are the ones that operated in the early universe. The continuity of physics across cosmic time is, by every careful comparison, complete in this regime. The interactions and reaction rates we measure in laboratories today are the same interactions and reaction rates that operated in the cosmic plasma at 1 second of age. The cosmic application of these laboratory-measured rates is what allows us to calculate with high precision what was happening in the universe at that moment. Let's talk about baryogenesis next. This is one of the deepest mysteries in early universe cosmology. The standard Big Bang model predicts that in the very early universe, matter and antimatter should have been produced in equal amounts. Particles and their antiparticles should have annihilated each other through high-energy collisions, leaving only radiation. The universe today should be empty of matter, filled only with photons and neutrinos. But the universe we observe is not empty of matter. It contains stars, galaxies, planets, and life. The matter has to come from somewhere. The standard explanation is that, in the early universe, some process produced a slight excess of matter over antimatter. The exact amount of the excess is, by every careful measurement, approximately 1 extra particle of matter for every 10 billion pairs of matter and antimatter. After the matter-antimatter pairs annihilated, leaving photons, the small excess of matter remained as the matter we observe today. The process that produced this asymmetry is called baryogenesis. The basic theoretical framework was developed by Andrei Sakharov in 1967. Sakharov identified three conditions that any baryogenesis mechanism must satisfy. First, baryon number must be violated. That is, the total number of baryons in the universe must not be conserved by the fundamental interactions. Second, charge conjugation symmetry and CP symmetry must both be violated. That is, the laws of physics must distinguish between matter and antimatter. Third, the universe must depart from thermal equilibrium during the relevant process. Without all three conditions, baryogenesis cannot produce a net asymmetry. The standard model of particle physics by itself does not satisfy these conditions strongly enough to explain the observed asymmetry. CP violation has been observed in the standard model, particularly in the decays of certain types of kaons and B mesons. But the amount of CP violation in the standard model is, by every careful estimate, far too small to produce the observed baryon-to-photon ratio. Some additional source of CP violation beyond the standard model is required. Various theoretical mechanisms for baryogenesis have been proposed. One is called electroweak baryogenesis, which uses the electroweak phase transition as the source of departure from equilibrium and invokes new sources of CP violation to produce the asymmetry. Another is called leptogenesis, which produces an initial asymmetry in leptons that is then converted into a baryon asymmetry through electroweak processes. A third is called gut baryogenesis, which produces the asymmetry during the Gutti epoch. None of these mechanisms is, by every honest description, fully established. Each has theoretical advantages and observational tests. Each makes specific predictions for properties that can be measured in particle physics experiments or cosmological observations. The relative merits of the various proposals are still being evaluated. Recent experimental results have refined the constraints. The NA62 experiment at CERN has been measuring rare kaon decays with high precision, probing CP violation in the kaon sector. The Belle 2 experiment in Japan has been measuring CP violation in B meson decays. The LHCb experiment at CERN has been studying CP violation in charm meson decays. The T2K experiment in Japan has been probing CP violation in neutrino oscillations. Each of these experiments adds to the constraints on possible baryogenesis mechanisms. But here's the thing most people don't realize about baryogenesis. It is, by every careful estimate, the reason anything exists at all. Without the small matter-antimatter asymmetry produced during the first fraction of the first second, the universe today would be empty radiation. There would be no atoms, no stars, no planets, no life. The asymmetry is, in this sense, the most consequential parameter in cosmology. A slightly different value would have produced a completely different universe. The exact moment when baryogenesis occurred is, by every careful description, not known with certainty. It could have happened during the Gutti epoch, before inflation, in which case the asymmetry would have been preserved through inflation by some mechanism. It could have happened during the electroweak transition, in which case the asymmetry was produced in the first picosecond of cosmic history. It could have happened through leptogenesis at intermediate energies, with the lepton asymmetry being converted into a baryon asymmetry through electroweak processes. The detailed timing depends on which mechanism is correct. The cosmic moment of baryogenesis is one of the most active research areas in early universe physics. New experimental results, new theoretical proposals, and new cosmological observations are continually being added to the picture. The understanding will, by every careful estimate, continue to develop over the coming decades. For now, the asymmetry is, by every honest description, established as a fact, but the underlying mechanism remains uncertain. Andrei Sakharov, the Soviet physicist who first identified the three necessary conditions for baryogenesis in 1967, was a remarkable figure in 20th century physics. He was one of the principal architects of the Soviet hydrogen bomb in the 1950s. He later became one of the most prominent Soviet dissidents, advocating for human rights and nuclear disarmament. He received the Nobel Peace Prize in 1975, although the Soviet government did not allow him to travel to accept it in person. His 1967 paper on baryogenesis was, by every careful estimate, one of the most influential papers in 20th century cosmology, identifying the conditions that any successful theory of matter-antimatter asymmetry would need to satisfy. The Sakharov conditions taken together are quite restrictive. They require fundamental physics beyond the Standard Model, in the sense that the Standard Model alone cannot satisfy them strongly enough. They also require a specific kind of cosmic history, with a departure from thermal equilibrium at the right moment. The intersection of these requirements has, over the past several decades, generated a rich theoretical literature exploring various possibilities. Leptogenesis in particular has emerged as one of the more attractive options. The basic idea is that the universe initially produced an asymmetry not in baryons, but in leptons, particularly in neutrinos. Heavy, right-handed neutrinos, predicted by various extensions of the Standard Model, would have decayed asymmetrically in the early universe, producing more leptons than antileptons. Subsequent electroweak processes, called Sphaleron processes, would have converted some of this lepton asymmetry into a baryon asymmetry. The final baryon-to-photon ratio observed today would, in this picture, be a consequence of the original lepton asymmetry. The leptogenesis mechanism has several attractive features. It connects baryogenesis to neutrino physics, an area where there is active experimental work and significant recent progress. It naturally produces the observed level of asymmetry without requiring extreme fine-tuning. It connects the matter content of the universe to the properties of the small but non-zero neutrino masses that have been measured in oscillation experiments. The recent neutrino oscillation experiments are providing important data for the leptogenesis hypothesis. The T2K experiment in Japan and the NOVA experiment in the United States have been measuring CP violation in neutrino oscillations. The current data, while not yet conclusive, hints at substantial CP violation in the lepton sector. If confirmed, this CP violation would be the source of the asymmetry that leptogenesis requires. The upcoming DUNE experiment, scheduled to begin operations in the late 2020s, will measure neutrinos' CP violation with much higher precision, and either confirm or rule out leptogenesis as the source of the observed baryon asymmetry. Electroweak baryogenesis, the alternative mechanism, would have occurred during the electroweak phase transition. For this mechanism to work, the phase transition must be sufficiently first-order, meaning there must be a clear separation between the symmetric and broken symmetry phases, with a phase boundary that moves through space. The Standard Model electroweak transition is, by every careful calculation, a smooth crossover rather than a first-order transition, so the Standard Model alone cannot support electroweak baryogenesis. Extensions of the Standard Model with additional Higgs particles or other new physics can produce a first-order transition, allowing electroweak baryogenesis to work. Future precision measurements at the LHC and at proposed future colliders will probe whether the electroweak transition in the early universe was first order or crossover. The Higgs self-coupling, which can be measured with sufficient precision at the high luminosity LHC and at future Higgs factories, is particularly informative about this question. If the Higgs self-coupling differs significantly from its standard model value, that would support a first-order electroweak transition and would make electroweak baryogenesis viable. The eventual resolution of the baryogenesis question will, by every careful estimate, come from a combination of precision measurements at particle accelerators, observations of neutrino properties, and cosmological observations of the early universe. The picture is gradually becoming clearer, with multiple converging lines of evidence narrowing the possibilities. By the end of the 2030s, we may, by every careful estimate, have a much more definite answer to the question of how the matter-antimatter asymmetry arose. Let's consider neutrino decoupling next, because it is the event that essentially defines what the universe looked like at exactly 1 second after the Big Bang. Throughout the first second, the universe was hot and dense enough that all the standard model particles were interacting frequently with each other. Photons, electrons, positrons, neutrinos, antineutrinos, and the few protons and neutrons all collided and reacted with each other, maintaining a thermal equilibrium across all species. As the universe expanded and cooled, the rate of interaction slowed. Eventually, the interactions became too slow to maintain equilibrium for some particle species. Those species decoupled from the rest of the cosmic plasma and began to evolve independently. Neutrinos were the first species to decouple. Neutrinos interact only through the weak force and gravity, both of which are very weak. As the temperature dropped to approximately 1 MeV, or about 10 billion Kelvin, the weak interaction rate of neutrinos became too slow to keep them in equilibrium with the other particles. Neutrinos froze out of thermal contact with the rest of the universe. This neutrino decoupling occurred at approximately 1 second after the Big Bang. The exact moment depends on the detailed thermodynamics of the early universe, but the standard cosmological calculations place it at almost exactly 1 second. This is, in many ways, what makes the 1 second mark cosmologically meaningful. Before 1 second, neutrinos were in equilibrium with the rest of the cosmic plasma. After 1 second, they were freely propagating, with their thermal distribution frozen at the moment of decoupling. The neutrinos that decoupled at this moment have, by every careful theoretical estimate, continued to propagate through the universe ever since. They form what cosmologists call the cosmic neutrino background, analogous to the cosmic microwave background, but consisting of neutrinos instead of photons. The cosmic neutrino background should be, by every careful theoretical prediction, slightly cooler than the cosmic microwave background, because the CMB was heated by the subsequent annihilation of electrons and positrons while the neutrinos had already decoupled. The predicted temperature of the cosmic neutrino background is approximately 1.95 Kelvin, compared to the cosmic microwave background's 2.725 Kelvin. The exact ratio depends on the specific cosmological parameters, but the prediction is quite robust within the standard cosmological model. Detecting the cosmic neutrino background directly is, by every careful estimate, extremely difficult. Neutrinos interact only through the weak force, and at the very low energies of the cosmic neutrino background, the interaction cross-sections are tiny. Detecting individual cosmic background neutrinos would require massive detectors of unprecedented sensitivity. No direct detection has been achieved as of 2026. Indirect evidence for the cosmic neutrino background, however, is strong. The Planck satellite measurements of the cosmic microwave background are sensitive to the number of relativistic species in the early universe, which depends on the presence of the cosmic neutrino background. The Planck data is, by every careful analysis, consistent with the predicted 3 species of cosmic background neutrinos. Big Bang nucleosynthesis calculations also depend on the neutrino background and are consistent with the predicted properties. The Ptolemy experiment, a planned future detector, is being designed to attempt direct detection of cosmic background neutrinos. The detector would use a target of tritium, which captures neutrinos through inverse beta decay. The energy released in each capture would be characteristic of the cosmic neutrino background, allowing it to be distinguished from other neutrino sources. If Ptolemy succeeds, it would be a direct confirmation of the cosmic neutrino background and a precise test of the early universe physics that produced it. But here's the thing most people don't realize about neutrino decoupling. The neutrinos that decoupled at 1 second after the Big Bang are still drifting through us today, right now, as you sit and listen. Every cubic centimeter of space contains approximately 340 cosmic neutrinos. Every second, trillions of these neutrinos pass through your body without interacting. They have been propagating freely since the universe was 1 second old, almost 14 billion years ago. Each one is, in some sense, a direct fossil of the moment of neutrino decoupling. The cosmic neutrino background is, in this sense, our most direct connection to the very early universe. The cosmic microwave background was emitted at about 380,000 years after the Big Bang. The cosmic neutrino background was emitted at 1 second. The neutrinos give us, in principle, a window onto a much earlier cosmic moment than the CMB does. If we can ever detect them directly, we will have direct experimental access to the universe at 1 second of age. The Ptolemy experiment, in particular, has been designed specifically to attempt this measurement. Ptolemy stands for the Princeton Tritium Observatory for Light, Early Universe, Massive Neutrino Yield. The detector concept involves a thin film of tritium, a radioactive isotope of hydrogen with a single proton and 2 neutrons in its nucleus. When a cosmic background neutrino interacts with a tritium nucleus through inverse beta decay, the tritium converts to helium-3 and emits a fast electron. The energy of the emitted electron is shifted slightly upward from the standard tritium decay endpoint, with the shift corresponding to the neutrino's contribution to the reaction. The challenges of detecting cosmic background neutrinos are substantial. The cross-section for the inverse beta decay process at the very low energies of cosmic background neutrinos is extraordinarily small. Ptolemy would need to use approximately 100 grams of tritium to detect even a few events per year. The energy resolution of the electron detector needs to be at the millielectron volt level, far better than any current spectrometer. The background events from other neutrino sources and from standard tritium decay must be suppressed to extremely low levels. The Ptolemy collaboration has been developing the various components of the experiment over the past decade. The detector prototypes have demonstrated several of the necessary technical capabilities. The full experiment, if approved and constructed, would begin operations in the early 2030s. If it succeeds, it would be one of the most direct experimental probes of the universe at 1 second of age that has ever been attempted. The principle behind Ptolemy is, in some ways, elegant. Tritium beta decay produces electrons with a specific energy spectrum, with a maximum energy at the spectrum's endpoint. If a cosmic background neutrino is captured by a tritium nucleus, instead of the tritium decaying spontaneously, the resulting electron has an energy slightly above the endpoint. The difference between the neutrino capture peak and the endpoint of the normal beta decay spectrum is, by every careful estimate, exactly twice the neutrino mass. By measuring this offset, Ptolemy can detect cosmic background neutrinos and simultaneously measure their masses. The challenge is that the offset between the two features is, for any reasonable neutrino mass, much smaller than the energy spread of the beta decay spectrum. To separate the cosmic neutrino capture peak from the much more numerous regular decay events requires extraordinary energy resolution. The Ptolemy design uses a combination of magnetic transport, electromagnetic filtering, and quantum coherent detection to achieve the necessary resolution. Each of these techniques is, by every careful estimate, at the frontier of experimental physics. If Ptolemy succeeds, the cosmic neutrino background would become a directly observable cosmological probe, analogous to the cosmic microwave background, but with the difference that the neutrinos give us a window onto a much earlier cosmic moment. The CMB shows us the universe at 380,000 years of age. The cosmic neutrino background shows us the universe at 1 second of age. The detection would, by every careful estimate, transform our experimental access to the very early universe. Beyond Ptolemy, several other experimental approaches to cosmic neutrino detection have been proposed. The Katrin experiment in Germany, originally designed to measure the absolute scale of neutrino mass through tritium beta decay, has explored possible sensitivity to the cosmic neutrino background as well. Various other ideas, including detection through coherent elastic neutrino nucleus scattering and through neutrino capture on radioactive nuclei other than tritium, have been considered. None has yet produced a confirmed detection. The relic neutrinos themselves are, in the meantime, all around us. They have been propagating through space for almost the entire age of the universe. They pass through Earth and through our bodies without interacting in such enormous numbers that millions of them traverse each square centimetre of our skin every second. They are invisible to us, undetectable by any sensory means available to humans, but they are, by every theoretical estimate, real. They are the most ancient cosmic particles we are likely to ever observe, dating back to the moment when the universe was just 1 second old. Let's pause and consider what the universe actually looked like at exactly 1 second after the Big Bang. The temperature was approximately 10 billion Kelvin, or 10 to the 10 degrees. By way of comparison, the surface of the Sun today is about 6,000 Kelvin. The center of the Sun, where nuclear fusion occurs, is about 15 million Kelvin. The early universe at 1 second was hundreds of times hotter than the center of the Sun, with the entire universe at this extreme temperature, not just a small core. The composition of the universe at 1 second was, by every careful calculation, dominated by photons and neutrinos. There were also smaller numbers of electrons, positrons, protons, and neutrons. The electrons and positrons were nearly equal in number, with a small excess of electrons matching the small excess of protons. The protons and neutrons themselves were in a particular ratio set by the rates of weak interactions converting them into each other. The density of the universe at 1 second was approximately 400,000 grams per cubic centimetre. That is about 400,000 times the density of water. The early universe was, by every comparison with present-day matter, extraordinarily dense. Every cubic centimetre contained enormous amounts of energy, distributed across the various particle species in thermal equilibrium. The size of the observable universe at this moment is, by every careful calculation, a more subtle quantity. The universe as a whole was expanding rapidly. The portion of the universe that was in causal contact with any given point, often called the cosmological horizon, was approximately 300,000 kilometers in radius at 1 second. That is approximately the distance from Earth to the Moon today. The horizon at 1 second was, in this sense, very small by current standards. The universe outside the horizon was, of course, still there. It contained more space, more particles, more cosmic structure in the making, but it could not have been in causal contact with the central point at 1 second. The horizon defines what could affect or be affected by any local region. Within the horizon, the universe was in approximate thermal equilibrium, with the particles all interacting and exchanging energy. The cosmological horizon was, by the dynamics of cosmic expansion, growing over time. By 1 second after the Big Bang, the horizon had grown to about light-second size. By later times, the horizon would grow much larger. The horizon, at the moment of CMB emission, about 380,000 years after the Big Bang, would be about 380,000 light-years in size. The horizon today is about 93 billion light-years across. But here's the thing most people don't realize about the universe. At 1 second it was a remarkable place. Hot, dense and active beyond anything in the present-day universe. The fundamental forces had completed most of their phase transitions. The matter-antimatter asymmetry had been established. Quarks had been confined into hadrons. Neutrinos had just decoupled. The universe was on the threshold of Big Bang nucleosynthesis, which would soon produce the first atomic nuclei beyond hydrogen. In some sense, the universe at 1 second was already recognizable. The particles were the ones we know from the Standard Model. The forces were the ones we know from particle physics. The thermodynamic principles were the ones we use in laboratory plasmas. The cosmological model is, by every careful calculation, consistent with everything we know about subsequent cosmic evolution. The universe was set up to become what we see today. The universe at 1 second was also in some sense completely alien. The temperature was so high that no atoms existed. No solid matter was possible, no stars, no planets, no anything of the structures we see today. The cosmic plasma was the only state of matter. Particles were colliding, annihilating, and being created at enormous rates. The energy density was higher than anything in the present-day universe. The expansion rate was extreme. The whole cosmos was, in some sense, doing physics at energies and densities that nothing today can match in the brief moment between the end of inflation and the gentler conditions of the post-first-second universe. The numbers describing the universe at 1 second are, by every careful estimate, almost incomprehensible by everyday standards. 10 billion Kelvin is a temperature far beyond anything ever produced in human technology. The hottest temperatures achieved in particle accelerators are perhaps 1 trillion Kelvin or higher, but only in tiny droplets of plasma for unimaginably brief intervals. The early universe was at 10 billion Kelvin everywhere, for a sustained period with no walls or boundaries. The density of 400,000 grams per cubic centimetre is similarly extreme. A teaspoon of the universe at 1 second would have contained roughly 2,000 kilograms of matter and energy, more than the mass of a small car. The energy density was correspondingly enormous. Every cubic centimeter contained more energy than is released by a typical nuclear bomb. The expansion rate at 1 second was such that the universe was doubling in size every fraction of a second. The Hubble parameter, which measures the rate of cosmic expansion relative to size, was approximately 1 over a second. In modern cosmology, the Hubble parameter is approximately 1 over 14 billion years. The universe at 1 second was expanding 14 billion times faster, in relative terms, than it is today. The cosmic ingredients at 1 second are also worth dwelling on. The dominant constituents by energy were photons and neutrinos, in roughly equal contributions. The electrons and positrons, still in approximate equal numbers, contributed less to the total energy. The protons and neutrons, vastly outnumbered by photons, contributed even less. The complete inventory of standard model particles, weighted by their thermal occupation at 10 billion Kelvin, gives the precise energy density of the universe at this moment. For every proton or neutron present in the cosmic plasma, at 1 second, there were approximately 1 billion photons. This ratio, called the baryon-to-photon ratio, is one of the fundamental parameters of cosmology. It is approximately the same today as it was at 1 second of age, because the number of photons and the number of baryons have both been conserved since then, with the cosmic expansion equally affecting both species. The value of approximately 1 part in a billion is the cosmic signature of the matter-antimatter asymmetry produced earlier in the first second. Each species of particle was, at 1 second, in thermodynamic equilibrium with the others through frequent interactions. The number densities of each species were set by their masses, their statistical properties, whether bosons or fermions, and the cosmic temperature. At 10 billion Kelvin, all the standard model particles lighter than about 1 MeV were present in significant thermal abundance. Heavier particles, including muons, taus, and the heavier quarks, had already disappeared from the plasma at this stage. The particle physics of the universe at 1 second was, in this sense, dominated by the lightest species: photons, electrons, positrons, neutrinos, antineutrinos, protons, and neutrons. The protons and neutrons, despite being heavier than the other species, were present in numbers determined by the matter-antimatter asymmetry rather than by thermal equilibrium with photons. The total cosmic energy density was, by every careful calculation, about 400 million times the average mass density of the present-day universe. The expansion driven by this energy density was, by general relativity, the cosmic expansion that we observe in continuation today. The universe was, in some sense, simply doing the same thing it does today, just at vastly higher temperatures and densities. The same equations of general relativity that describe the universe's expansion today describe the expansion at 1 second. The same standard model particles that we study in laboratories today were the constituents of the cosmic plasma. The continuity between the universe at 1 second and the universe today is, by every careful description, the cornerstone of modern cosmology. Consider what the universe at 1 second of age would have looked like, hypothetically, to an observer. There were no observers, of course. Conscious beings did not exist for billions of years after this moment. But the thought experiment is useful for understanding the cosmic conditions. Such an observer would, by every careful description, not have been able to see anything in the conventional sense. The universe was opaque. Photons could not propagate freely through the dense plasma. They were constantly scattering off electrons. The view at 1 second would have been a uniform glow of thermal radiation with no distinct objects or structures visible. The wavelength of the dominant radiation would have been in the gamma-ray and X-ray range, far too energetic to be visible to anything resembling biological eyes. The pressure at 1 second was, by every careful estimate, enormous. The thermal pressure of a relativistic plasma at 10 billion Kelvin is so high that no material object could have existed within it. The pressure was uniform across the cosmos on the scales we care about, so there were no boundaries or surfaces for pressure to push against. The universe at 1 second was a uniform, hot plasma, expanding rapidly, with no internal structure on the macroscopic scales we are familiar with. The microscopic structure was, by contrast, very active. Particles were colliding at enormous rates. Each particle interacted with others billions of times per second. The interactions maintained the thermal equilibrium across the cosmic plasma. Energy was constantly being exchanged between different particle species. New particles were being created from collisions, while existing particles were being annihilated through other collisions. The cosmic plasma was, in some sense, a very busy state of matter, with intense microscopic dynamics underlying the smooth bulk properties. Let's talk about what happened after the 1st second. Once neutrinos decoupled and the universe entered the 2nd second, several important processes continued. The most significant was electron-positron annihilation. Below temperatures of about half an MeV, electrons and positrons could no longer be efficiently created by photon collisions. The existing electrons and positrons began to annihilate each other, producing pairs of photons. The annihilation released enormous amounts of energy into the photon gas, heating it relative to the already decoupled neutrinos. By the end of electron-positron annihilation, which occurred over a period of perhaps a few seconds, only the small excess of electrons remained. The number of remaining electrons matched the number of protons, ensuring that the universe was electrically neutral overall. The cosmic photon-to-electron ratio settled to approximately the value we observe today, about 1 billion photons for every electron. The electron excess that survived this annihilation phase is, in some sense, the same matter excess that was established by baryogenesis earlier in the 1st second. The baryogenesis process produced a slight excess of quarks over antiquarks and a corresponding slight excess of electrons over positrons. Both excesses survived the various annihilation processes that consumed the equal portions of matter and antimatter. The result, by the end of electron-positron annihilation, was a universe with the matter content we observe today. Every proton matched by an electron, with no net electric charge, and with an extreme overabundance of photons relative to baryons. Without baryogenesis at earlier times, the electron-positron annihilation would have left behind no electrons at all. The universe would have continued to expand and cool as pure radiation, with no opportunity for atoms to form, for stars to burn, for galaxies to assemble. The fact that we exist as material observers is, in some sense, a direct consequence of the small matter asymmetry established in the very early part of the 1st second. The photons that emerged from electron-positron annihilation had, by every careful calculation, slightly higher energy than they would have had without the annihilation. The total cosmic photon energy was boosted by the energy released from the matter-antimatter annihilation. The cosmic neutrino background, having already decoupled before the annihilation, was not heated by this process. This is why the cosmic neutrino background is predicted to be slightly cooler than the cosmic microwave background today. After electron-positron annihilation completed, the universe entered the period of Big Bang nucleosynthesis. Beginning at about 3 minutes after the Big Bang and lasting for about 20 minutes, the protons and neutrons that existed in the universe combined into the first atomic nuclei beyond hydrogen: deuterium, helium-3, helium-4, lithium-6, lithium-7, and traces of beryllium-7 were produced. The exact abundances depend on the cosmological parameters, particularly the baryon-to-photon ratio and the number of neutrino species. The predictions of Big Bang nucleosynthesis agree, by every careful measurement, beautifully with the observed primordial abundances of the light elements. Hydrogen is approximately 75% of all the baryonic matter in the universe. Helium-4 is approximately 25%. Deuterium, helium-3, and lithium are present in trace amounts. The agreement between theory and observation is, by every careful estimate, one of the strongest pieces of evidence for the standard cosmological model. After nucleosynthesis, the universe continued to expand and cool. About 380,000 years after the Big Bang, the temperature dropped low enough for atomic hydrogen to form. Electrons combined with protons to make neutral hydrogen atoms. The universe became transparent to radiation. The photons that had been scattering off the free electrons could now propagate freely. These photons are what we observe today as the cosmic microwave background. The history from the first second onward is, by every careful estimate, well established. The detailed predictions of the standard cosmological model match the observed properties of the cosmic microwave background, the light element abundances, the large-scale structure of galaxies, and many other observations. The first second is, by comparison, less well established. We have good general theoretical frameworks for what happened during the first second, but the detailed mechanisms of inflation, baryogenesis, and the various phase transitions are not all fully understood. Big Bang nucleosynthesis in particular has been one of the most precisely tested predictions of the standard cosmological model. The model predicts specific abundances of the light elements based on a small number of parameters, including the baryon-to-photon ratio and the number of light neutrino species. The observations of primordial deuterium, helium-3, helium-4, and lithium-7 give independent measurements of these parameters. The fact that the various measurements are consistent with each other is, by every careful estimate, one of the strongest pieces of evidence for the standard cosmological framework. The deuterium abundance, in particular, is sensitive to the baryon-to-photon ratio. Recent measurements of deuterium in high-redshift quasar absorption systems give the baryon density to better than 1% precision. The measurement is consistent with the baryon density inferred from cosmic microwave background observations. The agreement between these two independent measurements, made using completely different techniques and probing the universe at completely different cosmic epochs, is, by every careful estimate, a powerful confirmation of the standard cosmological model. The lithium abundance, in contrast, shows a puzzling discrepancy. The observed lithium-7 abundance in old metal-poor stars is approximately 3 times lower than the Big Bang nucleosynthesis prediction. This lithium problem has been the subject of considerable investigation over the past 2 decades. Various proposed explanations include stellar destruction of lithium in old stars, new physics affecting the early universe, and systematic uncertainties in either the measurements or the nuclear reaction rates used in the calculations. The lithium problem remains, by every honest description, partially open. After Big Bang nucleosynthesis completed at about 20 minutes after the Big Bang, the universe continued to expand and cool. The cosmic plasma remained ionized for hundreds of thousands of years, with electrons freely interacting with photons through Thomson scattering. The universe was, during this period, opaque to radiation. Light could not propagate freely. It scattered off the free electrons at every step. This long, opaque period, lasting from about 20 minutes to about 380,000 years after the Big Bang, was, in some sense, an extended consolidation of what had been set up in the first second. The cosmic plasma cooled gradually. The various particle species settled into their long-term equilibrium ratios. The cosmic structure, encoded in primordial fluctuations, continued to grow under gravity. The universe was, throughout this period, in a state that was very different from the present-day cosmos, but recognizably continuous with the conditions established at the end of the first second. The temperature evolution during this period followed the standard cosmological expansion equations. From about 10 billion Kelvin at 1 second, the temperature dropped to about 1 billion Kelvin at 3 minutes, when nucleosynthesis began. By 20 minutes, when nucleosynthesis ended, the temperature was approximately 100 million Kelvin. The temperature continued to fall over the subsequent hundreds of thousands of years, eventually dropping to about 3,000 Kelvin at the moment of recombination. The energy density of the cosmic plasma was, throughout this period, dominated by radiation rather than matter. Photons and neutrinos contributed most of the energy density. The baryonic matter contributed a small fraction. The dark matter, although gravitationally important, did not interact significantly with radiation and was effectively a separate component. The cosmic dynamics during this radiation-dominated epoch were determined primarily by the radiation density, which was decreasing as the universe expanded. At about 380,000 years after the Big Bang, the temperature dropped low enough for electrons to combine with protons to form neutral hydrogen atoms. This event, called recombination, made the universe transparent to radiation. The photons that had been scattering through the plasma could now propagate freely. These photons are what we observe today as the cosmic microwave background. The CMB is, by every careful measurement, a thermal radiation field at a temperature of 2.725 Kelvin, with the characteristic spectrum of a blackbody at that temperature. The cosmic microwave background carries imprints of the conditions in the early universe. The temperature variations across the sky at the level of 1 part in 100,000 encode the pattern of primordial density fluctuations established during inflation. The polarization of the radiation encodes additional information about the conditions at recombination and about any gravitational waves present in the early universe. The detailed analysis of CMB data has produced, by every careful estimate, the most precise cosmological parameters available. The combination of CMB observations, light element abundance measurements, and large-scale structure surveys has produced the standard cosmological model that we use today. The model fits the data with remarkable precision. The parameters of the model, including the Hubble constant, the matter density, the baryon density, the dark energy density, and the amplitude of primordial fluctuations, are now measured to fractional precisions of a few % or better. The model has been tested across an enormous range of cosmic distances and times, and it continues to pass each new test. The successful predictions of the standard model in the post-first-second regime give us strong confidence in the framework that applied during the first second itself. the same general relativity, the same standard model of particle physics, the same statistical mechanics of relativistic plasmas, all applied in the first second as in subsequent epochs. The continuity of physics gives us a basis for extrapolating backward from the well-tested regime into the more speculative early universe regime. The areas where the standard model is less well tested, including inflation and baryogenesis, remain the active research frontier. Each new observation that constrains these areas helps refine the picture. The next several decades of cosmological observations will, by every careful estimate, gradually fill in the remaining gaps. The future cosmic microwave background experiments, including the Simons Observatory and CMB-S4, will measure the inflationary signal with much higher precision than is currently available. Future neutrino experiments will probe the lepton sector CP violation that may be responsible for baryogenesis. Future particle accelerator experiments will probe the Higgs sector for hints of new physics relevant to the electroweak transition. By the late 2030s, the picture of the first second may be, by every careful estimate, much more complete than it is today. The basic framework is unlikely to change. The detailed mechanisms will be increasingly well characterized. The cosmological parameters established in the first second will be measured to even higher precision. The connection between the first second and the present-day universe will be even more thoroughly understood than it already is. But here's the thing most people don't realize about the importance of the first second. Everything that happened later in cosmic history was set up by what occurred in that first second. The cosmological parameters established by the early universe processes determined whether galaxies could form, whether stars could ignite, whether planets could orbit stars, whether life could emerge on those planets. The matter-antimatter asymmetry determined whether anything would exist at all. The cosmic expansion rate, the dark matter content, the precise spectrum of primordial density fluctuations all were established in the first second. The first second of the universe is, in this sense, the most consequential second in cosmic history. The 14 billion years that followed have been, in some sense, an extended playing out of what was set up in that single second. Every star that has ever burned, every galaxy that has ever formed, every planet that has ever orbited a star, every conscious observer who has ever asked questions about the cosmos, all owe their existence to what happened in the first second after the Big Bang. The detailed connection between the first second and the present-day cosmos can be traced through specific cosmological parameters. The matter-to-radiation ratio, established by baryogenesis and the subsequent annihilation processes, determined when matter began to dominate the cosmic dynamics. The dark matter density, established by some process during the first second, whose details are still unknown, determined how cosmic structure would form. The amplitude of primordial density fluctuations set during inflation determined the eventual sizes of galaxies and clusters. The exact value of the cosmological constant, or of whatever drives the late-time cosmic acceleration, was either set in the first second or has been constant from the very beginning. Each of these parameters could, in principle, have had a different value. A different baryon-to-photon ratio would have produced different abundances of light elements during Big Bang nucleosynthesis, with cascading effects on the subsequent formation of stars and galaxies. A different dark matter density would have produced different cosmic structures. A different amplitude of primordial fluctuations would have produced a universe either too smooth for galaxies to form or too clumpy for stable cosmic structures to develop. The values that nature chose for these parameters are, by every careful comparison, exactly what is needed for the universe to contain stars, galaxies, planets, and life. Whether this is a coincidence, a consequence of some deeper principle, or an indication of multiple cosmic histories from which we observe the one compatible with our existence, is one of the deepest open questions in cosmology. The anthropic principle, the multiverse hypothesis, and various string theory proposals all address this question from different angles. None has yet produced a definitive answer. The fact that our universe contains observers patient enough to reconstruct the first second is, in some sense, the most striking consequence of the specific cosmological parameters. The universe we inhabit is one that, having been set up with the right parameters in the first second, has gone through 14 billion years of cosmic evolution to produce the conditions for self-aware observation of the cosmos. The first second is the origin of this entire chain, and the entire chain depends on the specific parameters that were established in that single second. Let's bring all of this together. The first second after the Big Bang was the most eventful second in the history of the universe. In that single second, the four fundamental forces of nature separated from a unified, grand unified force into the distinct forces we observe today. The universe underwent cosmic inflation, expanding by a factor of more than 10 to the 26 in roughly 10 to the minus 32 seconds. The electroweak symmetry broke, and the Higgs field gave mass to the fundamental particles. The quark-gluon plasma filled all of space before transitioning into a gas of hadrons. The matter-antimatter asymmetry was established through some baryogenesis mechanism, producing the slight excess of matter that allowed the universe to contain anything at all. Neutrinos decoupled from the rest of the cosmic plasma, forming the cosmic neutrino background that still drifts through us today. By the end of the first second, the universe was a hot, dense plasma of photons, neutrinos, electrons, positrons, protons, and neutrons at a temperature of approximately 10 billion Kelvin and a density of approximately 400,000 grams per cubic centimeter. The cosmological horizon was approximately 300,000 kilometers in radius. The cosmic neutrino background was already in place. The conditions for Big Bang nucleosynthesis, which would begin a few minutes later, were being established. The cosmic future was, by every careful estimate, largely set up. The experimental and theoretical work that has reconstructed the first second is, by every careful description, one of the great achievements of 20th and 21st century physics. Particle accelerators have reproduced conditions similar to those at the electroweak transition and the quark-hadron transition. Cosmological observations have provided detailed measurements of the cosmic microwave background, the light element abundances, and other cosmic relics. Theoretical frameworks, particularly the Standard Model of particle physics, general relativity, and inflationary cosmology, have provided the conceptual basis for understanding the early universe. The combined effort has produced, over the past several decades, a remarkably detailed picture of what was happening in those first instants. And we are, all of us, the generation that has reconstructed this picture. Before the 20th century, the universe was thought to be static and eternal. There was no concept of a Big Bang, no idea that the cosmos had a beginning, no understanding that the universe might have been in a vastly different state in the distant past. The development of general relativity, the discovery of cosmic expansion, the detection of the cosmic microwave background, the discovery of the Higgs boson, the measurement of the light element abundances, the development of inflationary cosmology, all of these were 20th and 21st century achievements. Our generation has, for the first time in human history, a coherent picture of the first second of cosmic history. Each piece of the picture was contributed by many different people working in many different fields. Theoretical physicists developed the conceptual frameworks, experimental physicists measured particle interactions and built increasingly powerful accelerators. Observational astronomers measured the cosmic microwave background and the abundances of cosmic relics. Cosmologists synthesized the various inputs into coherent models. The picture we now have is, by every honest description, the cumulative result of a multi-generational collaborative effort. The key milestones in the reconstruction of the first second can be traced through the history of 20th and 21st century physics. The development of general relativity by Albert Einstein in 1915 provided the mathematical framework for cosmic expansion. The discovery of cosmic expansion by Edwin Hubble in 1929 showed that the universe was not static. The development of nuclear physics in the 1930s and 40s gave the basis for understanding how light elements could have formed in the early universe. The Big Bang model itself was developed primarily by Georges Lemaitre in the 1920s and 30s, building on the equations of general relativity. George Gamow, Ralph Alpha, and Robert Herman, working in the 1940s and 50s, calculated the conditions of the very early universe and predicted the existence of a cosmic microwave background. The detection of the cosmic microwave background by Penzias and Wilson in 1965 confirmed the Big Bang model and won them the Nobel Prize in 1978. The development of the Standard Model of particle physics throughout the 1960s and 70s gave the basis for understanding what particles were present in the early universe and how they interacted. The discoveries of quarks, the W and Z bosons, the top quark, and the Higgs boson, each confirmed pieces of the Standard Model. The development of grand unified theories in the 1970s extended the Standard Model framework to higher energies. The development of inflationary cosmology by Alan Guth and others in the early 1980s provided the framework for understanding the very earliest moments. The development of quantum chromodynamics, the theory of the strong force, throughout the 1970s and 80s allowed detailed understanding of the quark-gluon plasma and the quark-hadron transition. The development of electroweak baryogenesis and leptogenesis theories in the 1980s and 90s gave possible explanations for the matter-antimatter asymmetry. Throughout the 20th and 21st centuries, increasingly precise observations of the cosmic microwave background by Kobe, W. Mapp, and Planck have refined our knowledge of the early universe. The discovery of cosmic acceleration in 1998, confirmed by multiple subsequent observations, added the cosmological constant, or dark energy, to the picture. The discovery of neutrino oscillations in the late 1990s revealed that neutrinos have non-zero masses, with implications for early universe physics. The cumulative effect of all this work is, by every careful estimate, a picture of the first second that is far more detailed and well supported than anyone in the early 20th century could have imagined. We have, in this sense, become the species that knows what happened in the first second of the universe. The picture is not complete, and significant open questions remain. But the framework is solid, the parameters are measured, and the major events of the first second are well characterized. And maybe that is the deepest part of tonight's story. The universe began. It went through an extraordinary first second. It then settled into the long 14 billion-year cosmic history that we observe today. We exist because of what happened in that first second. We can understand what happened because of the patient, theoretical and experimental work of generations of physicists. The first second is, in this sense, our origin story, written in the language of fundamental physics, decoded over the past century by careful scientific work. Every star we see in the night sky, every galaxy visible in deep telescopes, every atom that makes up our bodies, every photon arriving from the cosmic microwave background, every neutrino drifting through us from the cosmic neutrino background, all owe their existence to what happened in that single second. The first second is, by every careful measurement, where it all began. The hydrogen atoms in our bodies were assembled from protons that were produced in the first second through baryogenesis. The carbon, oxygen, and other heavier elements in our bodies were forged in stars that themselves formed from clouds of gas, whose composition was determined by Big Bang nucleosynthesis, which depended on conditions set in the first second. The energy that powers our daily lives trace back through the chain of nuclear fusion, gravitational collapse, and stellar evolution, comes ultimately from the energy density of the universe at 1 second of age. The connection extends to dark matter as well. Although we do not know what dark matter is made of, we do know that it makes up approximately 27% of the energy content of the universe, compared to about 5% for ordinary baryonic matter. The dark matter density was, by every careful estimate, established in the first second through some process whose details depend on what dark matter actually is. If dark matter consists of weakly interacting massive particles, they would have decoupled from the rest of the cosmic plasma at some specific temperature, leaving behind their thermal abundance. If dark matter consists of axions, they would have been produced through different mechanisms involving misalignment of axion fields. If dark matter consists of primordial black holes, they would have formed from density fluctuations during inflation. Each of these scenarios produces dark matter in the first second. Even the cosmological constant, the dark energy that is currently accelerating the expansion of the universe and will eventually determine its long-term fate, may have been set in the first second. The exact origin of dark energy is, by every honest description, one of the major open questions in cosmology. Some theoretical frameworks attribute dark energy to the vacuum energy of empty space, which would have been set at the moment of the electroweak transition or earlier. Other frameworks involve dynamic dark energy fields with values established during inflation. In either case, the value of dark energy that we measure today reflects conditions established in the first second. The first second is, in this sense, not just the origin of the matter and energy we observe today. It is the origin of the basic cosmological parameters that govern cosmic evolution. The framework within which 14 billion years of cosmic history played out was established in the first second. The specific values of all the fundamental quantities, from the masses of particles to the strengths of forces to the density of dark matter, were set in those first instants. When we look up at the night sky, we are seeing the long-term consequences of the first second. When we study fundamental physics in our laboratories, we are studying the rules that operated during the first second. When we exist as conscious observers asking questions about the cosmos, we are doing so in a universe whose properties were established in the first second. The connection is, by every careful estimate, direct and unbroken. The cosmic moment 1 second after the Big Bang is, in this sense, intimately connected to our present. The universe is, on every meaningful measurement, the same universe today as it was at 1 second of age, just expanded and cooled enormously. The fundamental physics has not changed. The fundamental particles are the same. The fundamental forces are the same. What has changed is the energy scale, the density, the size, and the dominant constituents. The continuity is, by every careful estimate, complete. This continuity is what makes cosmology a real science. We can extrapolate backward from present-day observations to early universe conditions because we know the rules of physics have not changed. We can predict the consequences of early universe processes for the present-day universe because the same physical laws apply throughout. The cosmic timeline is, in this sense, a single, coherent story from the first second to the present. Without this continuity, cosmology would be impossible. We would have no way to connect what we observe today to what happened in the past. The fact that the same physics describes laboratory experiments, the cosmic microwave background, and the very early universe is, by every careful estimate, one of the most remarkable features of our universe. It is, in some sense, what allows us to know anything about the first second at all, and we are, all of us, the generation that has come to understand this remarkable second. Before the 20th century, the question of what happened at the beginning of the universe was a matter for philosophers and theologians, not scientists. There was no observational evidence about the early universe. There were no theoretical frameworks for cosmic origins. The Big Bang was not a concept anyone had developed. The early universe was, by every honest description, completely unknown. Over the course of the 20th century, this changed dramatically. General relativity gave a mathematical framework for cosmic expansion. Hubble's observations confirmed that the universe was expanding. The Big Bang model emerged from these foundations. The cosmic microwave background was predicted and then detected, confirming the hot, dense early phase. The standard model of particle physics provided the inventory of particles that filled the early universe. Inflationary cosmology gave a framework for the very earliest moments. The first second went from being unknown to being one of the best characterized epochs in cosmic history. Our parents lived through some of this transformation. Our grandparents grew up in a world where the Big Bang was just an emerging idea. Our great-grandparents had no concept of cosmic expansion. The transformation in our understanding of the first second has happened, in some sense, in living memory. We are, in this sense, the generation that has fully assembled the modern picture of cosmic origins. The picture will continue to develop. Each new generation will add to it. Future cosmologists will refine the details, characterize the mechanisms more precisely, and possibly identify entirely new aspects of the first second that we have not yet thought to look for. The work is, by every honest description, never finished, but the basic framework, the major events, and the cosmological parameters established in the first second are, by every careful estimate, well characterized by now. Sleep well tonight. The first second of the universe is, in some sense, still echoing through the cosmos today. The cosmic microwave background, the cosmic neutrino background, the matter that makes up everything we observe, all are direct consequences of what happened in those first instants. The 14 billion years that have passed are, in some sense, the extended unfolding of what was set up in that single second. The story is, by every careful estimate, far from complete. Significant open questions remain. The exact mechanism of inflation, the specific identity of the inflaton field, the precise nature of dark matter, the underlying source of dark energy, the detailed mechanism of baryogenesis, the role of quantum gravity in the very earliest moments, all are topics of active research. Each of these questions, when answered, will refine our understanding of the first second further. The picture we have today will be deeper and more detailed by the end of the 2030s. But the basic framework is, by every careful estimate, established. We know what happened in broad outline. The exact details are being filled in. The first second is no longer a complete mystery. It is a specific cosmic moment with measurable consequences, a regime where multiple converging lines of evidence have produced a coherent picture, a time period whose major events have been characterized at progressively higher precision over the past several decades. The work continues. The Large Hadron Collider continues to probe particle physics at the electroweak scale. The Planck data continues to be reanalyzed for additional cosmological information. New cosmological surveys like DESI and Euclid are mapping the universe at higher precision. Future colliders are being designed. Future cosmological observations are being planned. Each new dataset will add to the picture. The international scope of this work is, by every measure, remarkable. Particle physics laboratories on multiple continents collaborate on shared experiments. The LHC at CERN involves contributions from dozens of countries. The Fermilab program in the United States, the KEK laboratory in Japan, the various European astronomy projects, the South African and Australian radio observatories all contribute different pieces of the larger picture. The data from these various facilities is analyzed by international teams with results published in scientific journals that are read by researchers worldwide. The connection between the first second and modern experimental physics is, in some sense, what makes this work meaningful. We are not just speculating about distant cosmic events. We are testing specific theoretical frameworks against laboratory data. The Higgs boson observed at the LHC has the same properties as the Higgs field that operated in the first second of cosmic history. The W and Z bosons produced in particle collisions today are the same particles that carried the weak force in the early universe. The quarks and gluons in heavy ion collisions are the same particles that formed the early cosmic plasma. This direct connection between laboratory and cosmos is, by every careful estimate, one of the most powerful aspects of modern fundamental physics. We can study the first second of the universe by doing experiments in laboratories on Earth. We can verify cosmological theories by measuring particle properties. We can constrain models of cosmic inflation by looking at the cosmic microwave background. The convergence of laboratory and cosmological evidence is what gives the modern picture of the first second its solidity. Without this convergence, the first second would be purely a speculative topic, with no way to test any specific theoretical claim. With it, the first second is a regime that can be probed by multiple independent observational and experimental approaches, with the results consistent with the standard cosmological framework. The agreement is not perfect, and important questions remain, but the basic framework is, by every careful estimate, on firm ground. The first second of cosmic history is, in this sense, no longer the impenetrable mystery it was a century ago. It is a specific epoch with measurable consequences. It is a time period whose major events have been characterized. It is the origin of the cosmological parameters that govern subsequent cosmic evolution. And it is, by every careful estimate, the most consequential second in the history of everything that has ever existed. Good night, and may your dreams reach toward the strangest second in the history of the universe, the moment when the four forces separated, when matter chose to exist instead of nothing, when the seeds of every cosmic structure were sown, when the cosmic neutrino background was set drifting through the space, when the seeds of every atom in your body were laid down, when the cosmos became the kind of place that could eventually, 14 billion years later, give rise to observers patient enough to reconstruct what happened in that first second after the beginning of everything.